All right, what is the definition of an ellipse? The definition of an ellipse is the set of points in a plane such that the sum of the distances from two fixed points is constant. So, let's say you have two fixed points, one over here. Fixed means it doesn't move. And one over here. And the length of the string is constant. So if you take all the points that satisfy this condition, you get an ellipse. Oh, that's ugly. And these two fixed points here, these are called the foci. And of course, the center is exactly halfway in between. This is called the major axis. This is called the minor axis. What do we call the endpoints of the major axis? Can you remember 1 year ago? The vertices. What do you call the endpoints of the minor axis? There's no real name for it. They're called the endpoints of the minor axis. I think that's what you guys did, your book did last year too. Okay, now how do you find all of these things? Okay, so this is what we need to go over. What are the standard equation of an ellipse? It's anyway, we did this in polar, remember? Coming up with these equations. But then now you're going to be responsible for knowing everything. So when you have a standard equation of an ellipse, there's a plus sign in the middle. If there was a minus sign in the middle, it would be a hyperbola, which we're going to learn on Monday, I suppose. And then you have these two numbers, a squared and b squared. A squared is always the bigger denominator. So if the bigger number comes under the x's, then the ellipse is this way. The major axis is horizontal. However, if the bigger number is under the y's, like this, see, if the bigger number is under the y term, then the ellipse is this way. The major axis is vertical. Now is it starting to ring a bell? Yeah, but Mr. Park, what's all this other stuff? Well, you can probably guess, what is HK? That's the center, just like circle, just like parabola. So the center is always located at the point HK. What is the meaning of this A and the B? Now remember, this is a squared and b squared. A is the distance from the center to the vertex. That's what A is. How should I draw this? That's A. Then of course by symmetry this is A as well, right? And you can probably guess B is the distance from the center to the endpoint of the minor axis. So this is B, and then of course by symmetry this would be B. And then, do you guys remember, what is the distance from the center to the focus? Let's go this side, like that. That's C. Yeah, but Mr. Park, there's no C in the equation. That's right. Okay, let's just pretend we don't know anything. So how do you figure out what C is? Well, in an ellipse, C squared is equal to A squared minus B squared. Okay, so this is what you learned last year. Learned in quotation marks. But see, the thing is, last year, you guys only learned like just a tiny bit of the ellipse. Because whenever you have a conic section, like a parabola, last night's homework, whenever you have a focus, there has to be a directrix on the other side. So if you have an ellipse, there's two foci. So that means there's going to be two directrices. You're going to have one directrix on this side and another directrix on this side. What would be the distance from the center to the directrix? You know what? I'm just going to tell you. A squared over C. In years past, we used to actually derive that, but we're not going to do it anymore. The main thing is you can find it. And then Do you guys remember this word from last year at all? Eccentricity? No. Anyway, eccentricity is basically a number that tells you the shape of an ellipse. Okay, so eccentricity is simply equal to C over A. We're not going to derive that either. So A, B, and C are just numbers. A is this, half the length of the major axis. B is half the length of the minor axis. C is the distance from the center to the focus. Every ellipse has these three numbers. To compute the eccentricity, you simply compute C over A. Now, if you look at this equation, out of the three letters, which one is always going to be the biggest? A, B, or C? A is always the biggest, right? Because you can change this around to A squared equal B squared plus C squared if you want to, right? Isn't that like the Pythagorean theorem? And the hypotenuse is always the biggest side of a right triangle, right? So A will always be the biggest. So if A is always bigger than C, then what can you say about the eccentricity? It's always going to be between 0 and 1 because A, B, and C are positive numbers. And what this does, it tells you the shape of an ellipse. The closer the eccentricity is to 0, the more the ellipse looks like a 0, like a circle. The closer the eccentricity gets to 1, the more it looks like a 1. So for example, if the eccentricity is like 0.01, that means it's going to be really circular. In fact, one of the applications of ellipses are their planet orbits. You guys learned that in physics, right? When the planets go around the sun, it's in the shape of an ellipse. And the eccentricity of the Earth's orbit around the sun is 0.01. It's almost 0, so it's very circular. But it's not a circle, it's still an ellipse. If the eccentricity is close to 1, like for example, 0.99, then the ellipse looks like that. It looks like a 1. So the eccentricity basically tells you the shape of an ellipse. Is it more circular or is it more like a hot dog? That's why we look at the eccentricity. So these are all the important parts. Oh, I forgot about the latus rectum. Now a parabola has a focus and a latus rectum, right? So an ellipse, since it has two foci, it's going to have two latera recta. Did I get that right, people in Latin? Is latera recta the plural of latus rectum? Who takes Latin here? I keep asking that question. It's nobody. Yeah? All right. So here's one latus rectum. Here is another latus rectum. You can see that by symmetry they both have the same length. Anyway, the length of the latus rectum in any ellipse is b squared over a. How do I write that? Here, just put length of lattice rectum. This is all in the notes, you know. Oh, I forgot to even mention the directrix. I didn't even drew it in. Oh, no, I did. The distance is a squared over c. So, Mr. Park, we got to remember all this stuff? Yeah, that's right. You got to remember c squared equals a squared minus b squared, c over a, b squared over a, and then a squared over c. Because that's how you find all the different parts of an ellipse. Okay, so what I'm going to do now, and this is supposed to be like the Algebra 2 review. We're going to take a specific ellipse and find all the parts. Because most of you just like forgot everything, right? All right. So then I'm going to erase. Well, don't worry about this AMC stuff because that's still 13 days away. Yes, question?
In the notes it says the length of the lattice rectum is 2b squared.
Oh yeah, 2b squared over a. You're right. My memory getting bad. Okay, so I got an equation of an ellipse over there. So let's write this down. 25x squared plus 9y squared. This is to make sure it comes out nice because, I mean, there's enough algebra as it is. We don't want it coming out ugly, yeah? minus 54y minus 44. So how can you tell this is an ellipse from the general equation? Just by looking at it. Remember, general form means make one side 0, throw everything else on the other. How do we know it's an ellipse just by looking at these two terms?
The coefficients are different, but have the same sign.
Exactly, they're different, but they have the same sign. If they were, like if it was 25 and 25, that's a circle. If that was a minus sign there, hyperbola. If you only have either x squared or y squared, then it's a parabola. Or we can use the thing we learned yesterday. What was the thing we learned yesterday? B squared minus 4ac. So there's no xy term, so b squared is 0. B squared minus 4ac. Is this number positive, negative, or 0? It's negative, so that means it's an ellipse. Remember b squared minus 4ac? If b squared minus 4ac comes out positive, then it's a hyperbola. That's the next lesson. Okay, so what we need to do is we need to put this into standard form. So we need to complete the square. So look at the x terms. Factor out the 25. Whatever the coefficient of x squared is, that's what you factor out. X squared plus 4x, leave a space. Now look at the two y terms. Factor out the 9, what's left? Y squared minus 6y, leave a space. Throw the number on the other side. Okay, what number do I have to add right there to make a perfect square? 4. Well, what did I actually add? 25 times 4 is 100. Make sure you add that to both sides. Now what about right there? 9. Take half of that number and square it. 9. What did I actually add? 81. Make sure you add that to both sides. Now we're in business. Uh, 225. Now remember, what is the standard equation of an ellipse? We did this when we did polar. What do we want this number to be? 1. So how do I make this a 1? Subtract 224 from both sides? Or divide by 225? You divide. Okay, now what happens when you divide this one by 25? Well, 25 goes into 225 9 times, right? Because 9 quarters is $2.25. Plus y minus 3 squared over 9 goes into 225 25 times. See? Standard form. So you can see right away, where is the center of this ellipse? Is it negative 2, 3, or 3, negative 2? I told you guys, the x goes with the x, the y goes with the y. It's negative 2, 3. That's the center. The bigger number is a squared, and the smaller number is b squared. So this is the a squared, and this is the b squared now. A squared is always the bigger number. If the bigger number is underneath the y's, that means the ellipse is up and down. Okay, so let's find out the parts. So you might want to draw a sketch here. So this is an up and down ellipse. Do we know the center? Let's draw the picture bigger. Okay, where's the center? The center is at negative 2, 3. Okay, here's the major axis, and here is the minor axis. So a squared is the bigger number, so that means a is 5, right? If this is b squared, b must be 3. Just remember, a, b, and c always have to be positive now. Okay, now, how do I find c? What's the equation that relates everything in the ellipse? C squared equals a squared minus b squared. Why, do you think I'm going to have to give you a note card to remember all these formulas? I'll think about it. Sometimes I let them use a note card, one side only. Okay, so anyway, so c squared is equal to a squared minus b squared, which is 16, therefore c is. See how I make the problems come out nice? I don't want it to come out too ugly. Okay, that's all you need. This is all you need to figure out all the parts of an ellipse. Okay, so remember what A is. A is the distance from the center to the vertex. So here's one vertex. So if I go 5 up, where am I going to be?
-2,
-2, 8. If I go 5 down, where are you going to be? -2, -2. Now what about the endpoints of the minor axis? Well, that's B. So you have to go B to the left and B to the right. B is 3. So here's the center. If I go 3 to the left, where are you going to be? -5, 3. If I go 3 to the right, 1, 3. This is easy stuff. Now what about the foci? The foci always lie on the major axis now. So to get to the foci, what do? You gotta go 4 up from the center and 4 down. So what if I go 4 up? Where are you gonna be? -2, 7. You just gotta be able to add, people. -2, comma, go 4 down. -1. No, that's all you did last year. That's what you did last year. Because they never told you about eccentricity or directrices or latus rectum. But now we know about these things. So which one shall we do first? Let's compute the eccentricity. Eccentricity is equal to C over A. So what is C over A? 4/5. Remember, eccentricity is simply a number. A number that tells you whether the ellipse is more circular or more hot dog-ish like. Okay, next let's do directrices. So if you have a focus, there's always going to be a directrix on the opposite side of right there. And then what was the distance from the center to the directrix again? A squared over C. So if this is A, what is A squared? 25. C is 4. That's like 6 1/4, right? So what would be the equation of the top directrix? Well, the y coordinate is 3 here. If I go 25 fourths up, where are you going to be? I'll give you a hint. 3 is the same thing as 12 fourths.
37.
Okay, thank you. So this would be y equal 27 fourths, right? It's a horizontal line. What's the equation of this directrix? Y equals... Okay, look, if you're at 3, which is 12 fourths, and then you go 25 fourths down, where are you going to be? -13 fourths. Did I do that correctly? 12, yeah, that's right. Okay, so those are the two directrices. Now what about the endpoints of the latera recta? So you have one latus rectum there, and one latus rectum there. So there's 4 endpoints of the latera recta. What is the length of the latus rectum? 2b squared over a. So let's see if we can do this in our head. What is b squared? 9 times 2? 18 over 5. So this is the length of the latus rectum. So half of that would be 9/5. So that means this is 9/5, this is 9/5, this is 9/5, this is 9/5. So to find the endpoints, you simply go from the focus, you go 9/5 left, 9/5 right. From this focus, 9/5 left, 9/5 right. I think you guys can do that, just to save time there, yeah? So right there, that's all the parts of the ellipse. So last year, you guys learned about half of them. But it was purged as usual. Okay, so this is kind of like a review of last year, but then what kind of problems are you going to get? Well, I think we better go to the examples. Woo! Okay, number 7 was just find all the important parts. Let's do number 8. Oh! That's what, you should actually go look at these examples before you do the homework. So that's what I'm doing for you, because it helps you. Mr. Parker, I see number 9. That's polar. I thought we were done with polar. No, we're just beginning. Okay, what does the problem say? Write the equation of the set of points P, X, Y such that the sum of the distances from these 2 points, well, it's up and down, yeah? So, -2, -3, and -2, 9 is 16. Okay, so let's say that this is a representative point on whatever graph we're talking about. You can probably guess it's an ellipse because it's on the ellipse worksheet, yeah? The sum of these 2 distances is 16. So one way to do the problem would be, well, Mr. Park, this distance plus this distance is 16. Well, how do I find this distance right here? Distance formula, right? So square root x plus 2 squared plus y plus 3 squared plus this distance. How do I find this distance? Square root x plus 2 squared plus y minus 9 squared equals, I forgot the number already, 16. So there's your equation. You write that down on your paper. If this problem is worth 8 points, I'll give you 2. But you want the rest, then you gotta put this into standard form. So, how do you deal with 2 radicals? Do I keep them both on the same side or should I separate them? Yeah, so I'm not gonna do this because this is outrageous to do it this way. You could take this one and move it on this side, square both sides, but you're still gonna have a radical, so isolate that radical, square both sides again, and then complete the square. How long would that take you? It's just algebra. It's 5 minutes maybe? Maybe 10? I don't know. Mr. Park, there's gotta be a better way. There is, but you gotta know stuff. The sum of the distances, they're not equal. The sum of these 2 distances is 16. Isn't that the definition of an ellipse? The sum of the 2 distances from 2 fixed points is constant. This is the definition of an ellipse. So if you know that, these 2 fixed points are the foci, which means the center is going to be halfway in between. So what point is halfway in between these 2? Using the midpoint formula?
-2, 3.
Okay, thank you. We got the center. We can write almost the whole equation. And which way does the ellipse go? Up and down or left and right? Since the foci are like this. It's an up and down ellipse, which means the y will come first. So then you go y minus 3 squared over a squared plus x plus 2 squared over b squared equals 1. See the bigger number under the y? Mr. Park, I don't know a and b. Yes, you do. You see this constant? What is that constant? I think I mentioned it in the beginning. 2a, because that's the way this equation was derived. I'm not sure if you guys covered the derivation last year. I know it was in the book. See, but you got to know that. And same thing with the hyperbola now. This constant is 2a. Oh, that means a is what? A is 8. And then, so of course then this is 64, right? And then, what is the distance from the center to the focus? That's C, right? What is this distance? 6. So we know C is 6. If you know A and C, can you figure out B? Yeah, if you know any 2 of them, you can find the third one by using, what was that equation again? C squared equals A squared minus B squared. So 36 is equal to 64 minus B squared. Therefore, B squared is, Mr. Park, I gotta borrow. I'm having a hard time. 28. There you go. That's the equation of the ellipse. So, would you rather do it this way, by knowing stuff, or do it this way by not knowing stuff? Because I don't really care. The main thing is you get this. But you gotta know stuff. That's the thing. That's the hard part. Okay, next problem. Polar. I gotta erase. We gotta stay on this side of the board. R equal 15 over 3 minus 2 sine. See, you guys are lucky. In previous years, we didn't even have time to go over these examples. All we had time to do is, remember the one I completed the square and we found all the parts of the ellipse? That's all we have time for, but that's because in class we had to go over like parabola. How many problems would you have had if I didn't do all the homework for you already? Probably 5 or 6 problems we had to go over, and then we hardly have any time to discuss it. So and then the cycle just begins again. Okay, what is the problem? It says, find the coordinates of the foci of this ellipse. Now, I'm not going to tell you this is an ellipse. However, look at the notes. See, we never went over everything in polar, but anytime you have an equation that looks like this or this, it's going to be a conic section. Okay, I guess I better write it down for the people watching on video. R equal EP. This is not the same P as in the parabola one. No? 1 plus or minus E cosine theta, or R equal EP, 1 plus or minus E sine theta. These are going to be conic sections, and you know how you can tell which conic section it is? You look at E. E stands for, we talked about this 5 minutes ago, eccentricity. So we already said if the eccentricity is between 0 and 1, it's going to be an ellipse, right? We talked about that already. If the eccentricity is equal to 0, 1, that will be a parabola. If the eccentricity is greater than 1, it's going to be a hyperbola. Here, let me do this. Ellipse, parabola, hyperbola. Okay, so looking at this equation, what is the eccentricity? Eccentricity is the number next to the sign, people. But then this number has to be a 1. So, is the eccentricity 2? No, it's 2/3. How do you make this number a 1? Divide top and bottom by 3, right? So that becomes a 2/3. So if the eccentricity is 2/3, which means it's less than 1, that means it's an ellipse. But it's the ellipse worksheet. It better be an ellipse, right? Okay, so we know it's going to be an ellipse. How do you find the foci? Well, one way is change it to a rectangular equation. Remember, like we did in last chapter? Okay, watch. Some of you are going to say, what? Okay, cross multiply. Hey, use somebody. That's y. Isolate the r, so you get 2y plus 15. Square both sides. 9r squared is equal to 4y squared plus 60y plus 225. And what is r squared equal to? X squared plus y squared. There you go. And then now complete the square, and then you can figure out the foci, right? But that's a lot of work, Mr. Park. There's a lot of algebra. Yeah, there is. Is there a faster way? Yeah, if you do what I tell you in the example. I'm going to erase this. Watch what I do. So, I'm thinking you probably could do this method in about 4 or 5 minutes. If you do what I'm going to tell you now, you can do it in less than 1 minute. Let's draw the graph. Okay, remember how to draw these graphs? Remember from polar? Plot the 4 quadrantal angles. Okay, plug in 0. Sine of 0 is 0. 15 over 3? 5. Undid plug at 10. Plug in pi over 2 now. Sine of pi over 2 is 1.
15.
So you get 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's just put 15 there for a reminder. Plug in pi now. Sine of pi is 0. So you're going to get 5. 1, 2, 3, 4, 5. And then plug in 3 pi over 2. Sine of 3 pi over 2 is negative 1. So you get 3. 1, 2, 3. Remember, we're graphing polar now. Now look at the placement of the 3 points. Here's Johnny. I kind of missed it, so just make the dot bigger. There's your ellipse. Okay, I guess you guys didn't read the example. Anytime an equation looks like this, see, this is the good thing, but you gotta know stuff. The focus is at the origin. One focus, no matter whether it's a parabola, ellipse, or hyperbola, one focus will always be at the origin. So, this is one focus. That's F1, 0, 0. How do I find the other focus? Yeah, just by symmetry, look. Here's the vertex. If I have to go 3 inward to get to this focus, then here's this other one. Don't I have to go 3 inward to get the other focus? So if this point was 0, 15, then what? 0, 12. Finished. Those are the two foci. In fact, let's do one more thing, because I remember putting this on last year's quiz. You just never know. Or is it a test? What about the directrices? Write the equation of the directrices. Can I do that, or should I just keep continuing with this to figure out A, B, and C? No, you got everything you need right here in the picture. Okay, where is the center? What's halfway between 0, 0 and 0, 12? 0, 6, right? 1, 2, 3, 4, 5, 6. Here's the center, 0, 6. Therefore, what do we know? How far is it from the center to the focus? C. C is 6. How far is it from the center to the vertex? That's A. A is 9. Isn't that all you need to figure out the directrix? How far is it from the center to the directrix? A squared over C. 81 over 6, which can be reduced to? Divide by 3. 27 over 2, which is 13 and a half. So to get from the center to the directrix, you simply got to go 13 and a half down, and then 13 and a half up. Okay, let's see if we can do that. If this distance is 27 over 2, what's the equation of this directrix? Y equal, the y coordinate up here is 6, which of course is 12 halves. If I go 27 halves down, what are you going to get? Negative 15 halves. What if you go 27 halves up? Y equal 39 halves. Oh! And there you go. Isn't that a lot better than doing this? See, the more you know, the easier math is. Otherwise, you're just memorizing all these things from all over that doesn't even relate. That's why maybe you guys purge so easily. And are we graphing a tilted ellipse something? Yeah, but you guys know how to do that. Just do advanced graphing. Everybody can do advanced graphing? Yep, that's it. Those are all the examples here. All right. Any questions on this ellipse? Mr. Park, this is just way more than we learned last year. No, it's pure calculus now. But you'll be happy to know that if you did purge this, it wouldn't be so bad, because in calculus we don't do conic sections. Oh, I almost forgot to tell you the most important part. Why do we study ellipses? Just so teachers have jobs? No, I already told you there's practical applications of it. I can't believe I almost forgot to tell you that. So one application is planet orbits, right? You guys know that from physics. When a planet goes around the sun, okay, here is the planet. It can be any planet. What planet do you want to use here? Venus. Okay, the sun is at one focus. See, Venus goes around the sun. What's at the other focus over here? Please don't say it. If the sun is at one focus, what's at the other focus? Okay, well, at least you didn't say what they said in the last 5 years. You know what they said? The moon. Are you kidding me? When the moon goes around the earth, it's in the shape of an ellipse. So the earth would be at one focus. What would be at the other focus? Nothing. There's nothing there. So the sun is at one focus and the planet goes around the sun like this. Anyway, that's why sometimes the planet is closer to the sun and then over here it's farthest from the sun, right? Anybody here in Science Bowl? No. When it's closest to the sun, I forget which is which. One of them is called aphelion. Helion means sun, right? Hey, helios. And the other is perihelion. Anybody want to help me out with that? Which one is the closest to the sun and which is farthest from the sun? Anyway, there's going to be a problem on this on tonight's homework. I'm going to give you the closest distance to the sun and the farthest distance from the sun, and then you have to tell me what the eccentricity is. What? You just have to know all the parts. It's not that difficult. The hard part is you got to know all the parts. The other application of an ellipse is this. Okay, here are the two foci. If you have sound waves or light waves or whatever emanating from one focus, it will hit the ellipse, and where do you think it's going to go to? The other focus. It goes like this. Gong gong, gong gong, gong gong, gong gong. And you know how to prove this if you had to prove it? Like right there. Didn't you guys learn here? Let's just do one over here. Gong gong. How do you know it's going to go to the other focus? Because in physics, don't you guys learn that the angle of incidence equals the angle of reflection? Or you didn't get there yet? Okay, you can impress your teacher later on then. Anyway, okay, so how can we use this in real life? Have you guys ever been to a whispering chamber? Like they have it in, like, I don't think they have it here, maybe somewhere in Hawaii, but if you go to museums on the mainland, they have what we call this whispering chamber. So what you do is you climb up a short stairs and then you stand over here. And then your friend or other family member is here, and you're far away. It's like I can be talking to somebody in the what building is that called? Sullivan Center. What is that? About 50 yards away, and you can be just talking like this, and you can hear each other perfectly. You know how? Because they have these things over here like this. So these are like the two foci of an ellipse. All the sound that goes over here goes to the other focus. You guys know, not one person experienced this before? Okay, where was this?
It was in the Capitol.
Oh! Statuary Hall, right? In the Capitol building. Okay, you guys took AP history this year or last year? Or just regular US history? Last year? Okay, I'm sure your teacher, because I saw the history book, and I know there's a picture of it. So your teacher must have told you the story. So I don't know what the two parties were, but John Quincy Adams? He's sitting here on this bench in Statuary Hall. And then the other party is over here. They're talking amongst themselves, whispering, but he could hear everything they were saying. You know why? Because Statuary Hall is in the shape of an ellipse. And those are the two, they purposely put the two benches like that where the foci are. So all the sound waves going on like that, it goes right to the other focus. And John Quincy Adams is just pretending to be asleep, but he can hear everything. Who's John Quincy Adams? And you know what's a medical application of this? I didn't know until I actually had kidney stones. Did anybody ever have kidney stones? You heard of it? You don't want it. It's so painful. It's so painful, you pretty much have to go to emergency because it's terrible. Anyway, so normally what happens is, let me think about the human body. You have a kidney, and then it drops into the bladder, right? So you have a kidney stone, and when the kidney stone moves, it's very painful. And then it drops into the bladder, and then what do you do from the bladder? You expel it. But the problem is, if the kidney stone is too big, it might not drop into the bladder. And then if it's really big, then how are you going to pee it out? I don't know, Mr. Parker, they'll just force it out. It's painful. So you know what they do? They blast up the kidney stone. You ever heard of that? It's called a lithotripsy. So what they do is they use shock waves. So, okay, here's your, okay, so this is what they did. So the doctor was describing it to me because I had kidney stone like 5 times already. Anyway, so they put you into this elliptical bath. This is a 3-dimensional elliptical bath, yeah? And of course they put you have anesthesia. So here's the 2 foci. So what they do is they place you here, and then I guess they can tell by either ultrasound or, yeah, it must be ultrasound. So they line up your where they think your kidney stone is. They put it at this focus, and then here is the shock waves. So all the shock waves go out. Now it's 3-dimensional, so it's going down too. It's like a big elliptical bowl like this. So all the shock waves go out, and it goes to the other focus like that. Boom, and then it just pow. Then it breaks up the kidney stone. So instead of a big one, you get like lots of small ones. Drops into the bladder, and then you pee it out. Your only other option then is to go in and have surgery. So this is a better way than having surgery, right? So yes, there are practical applications of this all over the place. That's why we study conic sections. Not just so teachers have jobs. It's ridiculous. Woo! Okay, any questions on this? And then next time I see you, we'll do the hyperbola. And then we're done. Wow, that took a long time. Only 5 minutes left.